Hi, my name is Jack, and this is my Week 10 project. I like to start with the results, so here's the graph, the plot that comes with my body. It's two frustrums, the top and bottom, with a rectangular rod in between them. The centroid of the figure is the origin as well, so it goes in the positive and the negative on either side symmetrically. I find the strain energy is the main thing I think at the end of the this week's project that we're solving for is that U total strain energy. Um, I verify by using the second body, the rectangular body, just because it was a little easier to verify with. And I found it to be 5.92 times 10 to the ninth joules. I'm looking at my work right there. And then this was just the total result. So let's look at the work and how we got there. First, I started by defining a deformation map for the week. That was the first objective of the week. Then the next step is to find the gradient of that so that you can then use this equation to find the strain. Here's our strain tensor. From our strain tensor, we can then use this equation. I have like this latex code that explains it as almost like a proof. Use the trace of the strain and the Poisson's ratio that is defined for this material. I show that definition a little later. I used the one from class, and the C, which I have defined is still the same as class, 200 times 10 to the 7th centimeter, or kilograms per centimeter times second squared. Um, so two main steps we come out of this with from the deformation map is the strain tensor and the stress tensor. From those, we can find the strain energy density, which is given by 1/2 times the summation of those 9 terms, which is shown here. A lot of them end up canceling out. We just kind of have to go through the tensors we solved for in the last one and say, hey, you strain 1, that's 0, multiply here, cross it out. So we go through and we find our terms and we simplify it down to equal this equation right here. Down here, quite literally the same exact thing as the latex code. It was just when I did it handwritten the first time to figure out what I was doing. This is more information on the body that we're dealing with. So the body's geometry becomes important the next step because we're going to plug that into that deformation matrix or density map. So this is the map we solved for on the last slide, and then this is once we plug in the actual geometry, what we're left with. The next step and the final objective for this week is to solve for the total strain energy. That is defined as the integral of the strain density map over the volume. Again, this is the equation we solved for in the last slide. So U is going to be the triple integral. I left du, dv, dw off of this. It got cut off, but this would be the equation. I then went ahead and applied like that's a geometry variable A for my body and things like L or geometry variables. So I went through, I did the handwritten work, and I plugged in those variables. Like you can see, I plugged in L is 10, so that step it goes in. And I get 5.92 times 10 to the 9 joules. We can go back to that is our final from the first slide and what we saw for in the MATLAB code. So that's all the work. And now I'm going to just verify with the MATLAB code. Here's the code. Run it. So there's our body. The stress applied, or the deformation applied. And then this is that value that we solved for that second body. All right, thank you.